Okay, this is my demo 6. You asked me to demo on 7C, and 7C states that I can design logic circuits for basic arithmetic operations such as add, subtract, multiply, compare. So my goal for this is to design a circuit that adds two 2-bit binary numbers. So I started out by making a truth table with 4 inputs, my A inputs and my B inputs. So pretty much all I did was I went through every combination of 0 and 1 for the 4 inputs. So and then added them together. So for 0, 0, 1, 0, the A1 and B1 will be 1, and then A0 and B0 will be 0. And so I just kind of went through that process for each one to figure out my 2 outputs. And so sum 1 is the output of A1 plus B1, and sum 0 is the output of A0 plus B0. And so yeah, I went through each one of those and was able to come up with my truth table. And so for the carry out, whenever there's a 1, that's because so like for this one right here, we're adding 0, 1 plus 1, 1. So that would be for the A's binary 1 plus for the B's binary or decimal 3. So that the output should be 4, but this doesn't go up to 4, so we'll have a 2 carry out of 1 pretty much. So that's my truth table. That's kind of the process I went through creating it. And then I made a K-map for my 3 outputs. So my sum 0, my sum 1, and my carry out. I'm not going to go into much depth about those. I'll explain mostly when we get to logics in my circuit. But the equation I got for sum 0 was A0 XOR B0. And then for my sum 1 equation, I got A1 XOR B1. And then the carry out equation was A0 and B0 or A1 and B1. So those are my 3 equations that I used to create my circuit. So here's my circuit that I designed. I have 4 inputs, my A0, B0, A1, B1. A1. Okay, so my 4 inputs and then my 3 outputs right here. And then my 3 equations that I got. And so we'll start with the XOR gate for the sum 0. So this one, let me go to this. So this one right here, it's not letting me click, sorry. This one right here is my XOR gate for the sum 0. The inputs that go into it are A0 and B0, and the operation for it is the XOR gate calculates the sum of A0 and B0, and this will be the value of sum 0. And that's true with our equation that we got. And the logic behind it is if A0 and B0 are the same or both are the same, either being both 0 or both 1, the output will be 0. And if they are different, the output will be 1. So if they are the same, like 0, 0, the output will be 0. If they are different, such as 1, 0 or 0, 1, the output will be 1. And you can see if they're both 1, they're the same, so the output is 0. That's the logic behind this XOR gate for the sum 0. And it's pretty much the same exact thing for A1 and B1. If they are the same, the output will be 0. And if one is different, then the output will be 1. So let's turn these off real quick. 1, 0, we get 1, 0, 1, we get 1, 1, 1, we get 0, because they're the same. So that's the operation and logic behind the two XOR gates, these two. And then we have our AND gates. Those are for the carry calculations. So for the first AND gate, the A1, B1, this AND gate checks if both A0 and B0 are 1. If they both are 1, the output will be 1, which indicates a carry from this bit position. So the output is A0 and B0. And the logic is this AND gate produces a 1 only when both A0 and B0 are 1. So if they're both 1, then we get a carry out of 1. So as you can see, they're both 1, carry out 1. So we'll turn off that, and that's the only time we get a carry out. So for this AND gate, for the A0, B0, it is it's the same operation. So if they are both 1, we get a carry out of 1. And you can see that is true. And then, okay, so then the OR gate for the final carry out right here, the inputs from the two AND gates, A0 and B0 and A1 and B1, this OR gate checks if either of the AND gates produced a 1, indicating a carry from either of the bit positions. If either one of or both are 1, the OR gate will output a 1. So we do that, and we can see that's true. So if either of them are a 1, we get a 1. So there we got a 1. There we got a 1. They're all 1s. We should still get a 1. And so the logic behind that OR gate ensures that if there's a carry from either of the bit positions, the carry out will be 1. If both AND gates output 0, so if both of these AND gates output 0, indicating no carry from both bits, the carry out will be 0. And so we look back at my equations, the sum of 0, A0 XOR B0, right here. We have that equation for sum of 0. Sum 1, the equation A1 XOR B1. And then, there should be carry out right here. Carry out equals A0 and B0 or A1 and B1. And so, yeah, that is the basic operation and logic behind the circuit. And so we can let me pull up the truth table real quick. So now we could test it. So we'll do an easy one first. We'll do 0, A1 and A0 are both 0. And then B1 is 1. And B0 is 0. So this is 0, 0 plus 1, 0, which will give us 1, 0, 0. Now let's test one that'll have a carry out. So if we have A1 is 0, A0 is 1, and then B1 and B0 are both 1, that's 0, 1 plus 1, 0, 1, 1, which will give us 1, 0, 1, because that's obviously higher than 3. So we get a 2 and then a carry out of 1. So we can see this circuit lines up with the truth table and is working good. So that is a 2-bit binary adder. And that is the end of my demo.